So in the last class, last week or last set of topics that we did, we spoke about decoder only models. In particular, we did a deep dive in GPT, the first version of GPT, and then we had a sort of takeoff from there and spoke about decoding strategies, right? And which are important from the perspective of generating text, and which is what is sort of wowing us about GPT, Chat GPT, and the other models which are coming out, right? So we looked at a bit of that. Today, what we are going to do is we are going to talk about yet another model which is a contemporary of GPT, at least the first version of GPT. It was called BERT, which is Bidirectional Encoder Representation from Transformers. And it was a very popular model. It came out around 2017, if I am not wrong, and sort of led to the evolution of an entire field called Bertology, right, where people are actually trying to study what are the different things learned by BERT model, what do the attention heads in BERT learn, what do the different layers of BERT learn, and so on. How can you prune BERT, what happens if you prune, and so on. Right? So it was quite popular for at least I would say 3 to 4 years after it came out, right, before this next generation of more powerful LLMs which are trained on much larger amounts of data and have much larger number of parameters came out, right. So again, a very seminal work. So we will look at it in the context of encoder only models, right. So this is where we were looking at decoder only models in the previous lecture. So today what we will look at is how to use the encoder of the transformer to sort of model a language model, right, to build a language model. So let's see how the discussion goes, right. So in the case of GPT, we were using what is known as causal language modeling. That means you feed the inputs left to right, and when you are predicting the current word, you only look at the history, you do not look at anything else which comes after us, right. But BERT was built with a slightly different intention, that you want to capture the essence of text, right, and in that case, if I look at words which come after the current word, that might also help, right. It might help in establishing relationships between a word and words which come before it as well as after it, right. So that was the sort of philosophy there. So this is what happened in GPT, right. So we had I like to, and then we wanted to predict the next word, which could be play, watch, go, read, whatever, right. Any of those words are likely. So this is a very natural fit for tasks like text generation, and this is by far more popular in the current generation of LLMs than these encoder only models like BERT, right. So most of the current large scale LLMs that we know about are decoder only models, right, or encoder decoder models, which we have not done yet. Right? But what about tasks like named entity recognition, right? So suppose in named entity recognition, you might depend on words which come after the current word in order to decide what kind of a named entity this word is, right? So I went from Delhi to Goa. So now this to Goa also helps in deciding that, okay, this might be yet another location named entity. Delhi might be a location named entity. So that's the motivation. That you should look at things which occur on both sides of the current word as opposed to only looking at the past history, right. And if you think of it, right, so if you are given a sentence, any word in the sentence would have relations with words before it as well as after it, right. If you look at languages like subject, object, verb, or subject, verb, object, if the object is in the middle, it has a relationship to the verb, it has a relationship to the subject. Similarly, even if the verb is in the middle, it has a relationship to the object, it has a relationship with the subject, even the subject is related to the object, and so on, right. So you would expect these what are known as bidirectional representations or bidirectional interactions, right. That's where the B comes from, bidirectional for BERT, right. And suppose this is a fill in the blank task, right. So Dash has shipped its new OS, right, to something else, right. So now in this case, based on everything that is coming after it, you can predict that this is a company because it has shipped something, right, and it has to be a company, right. So these kind of tasks, you may need context from both sides. So it makes sense to look at models which allow you to consume input from both the sides. So that was the basic idea behind BERT, and GPT was already out. I mean, as I said, it was a contemporary, so maybe a month or so or a few months ago GPT was already out, and then BERT in their motivation they say that, hey, this only looks at left to right context, but we would like to look at context on both sides. So how do you achieve that, right? So that's the question that they answer. How would you enable modeling context on both the sides? So for that they came up with something known as masked language modeling. So in the case of GPT, we had looked at causal language modeling. Now we look at masked language modeling, right? So let's see what that is. So now we need to look at both directions. I have said it enough times now already. So while predicting this blank, right, I dash to read a dash, I want to look at I as well as I want to look at what comes after it, which is to reader, right? So I want to predict the masked word using the context in both the directions. Setting this up is called masked language modeling, right? I mean, how do you set up this task? Now we cannot use a decoder component of the transformer as it is, at least the way we have studied it, right? In the original transformer model where you had an encoder and a decoder, and whatever we were referring to as a decoder, it always had this left to right dependency, right? You look at things on the left, then generate things on the right, then this also becomes left, and then you generate the next word and so on, right? So inherently it was something which looks at left to right, and hence in the causal language modeling it made sense, right? Because there also you are looking at left to right, right? But now you want to do something which is different, which looks at both sides, and that's not what the decoder inherently does, right? At least in its vanilla form, right? You can always train something new and call it a decoder, but in its vanilla form it did not look at that, right? So now can we use the encoder part of the transformer, right? So this is what the encoder looked like in our encoder decoder model, right? So the encoder was taking a sequence of inputs, then it had a series of these transformer blocks which had multi-head attention and feed-forward networks and the residual connections and normalization layers, right? So this is one block of the transformer and it had multiple such blocks, and at the end you had some representations coming out, right? So this is what the encoder looked like. There was no cross attention here, right? Because there is no input from anywhere else, it's just the encoder input. Now how do you use it? So this is what we are interested in knowing, right? So we are interested in P of yi given x1 comma xi is equal to something, right? So let's understand what we are trying to predict here. We are trying to predict the word at the ith position. The ith position is where you have masked input, right? Masked means you have sort of said this is a blank, or you have introduced a spatial token where you are saying this is a masked token. And now at the output, what do you want to do? You want to predict a distribution over the vocabulary, and hopefully the highest probability should be of the word which is the actual masked word, right? Suppose this was like. Suppose like was the word which was masked because my input was I mask to read mask. So I am predicting this mask, and maybe the actual word was like in my training corpus. So I want to maximize the probability of predicting like, right? So what I am interested in is that predicting the probability that the ith output is equal to like given the entire sequence that I have, right? Remember now it's the entire sequence x1 to xt, as opposed to in a causal language model where you have x1 to xi minus 1 or xk minus 1, right? Just up to the previous word, right? So this is how you are casting the problem now. This is the probability that you want to predict, okay? So let's go ahead from here, and of course it is assumed that the predicted tokens, right, the masks that you are predicting are independent of each other. That means if I have masked the second token and the 8th token and I have predicted something at the second token, then I don't use that information for predicting the 8th token. For the 8th token, still the second token is a mask, just as for the second token the 8th token was a mask, right? So you could think of a sentence which has 20 tokens, some 3 tokens have been masked out, and you need to predict these 3 tokens by just looking at the remaining 70 tokens, and you are not doing this sequentially. That means you are not predicting the second token first and then the 8th token which was masked now knows 18 tokens as opposed to 17 tokens which were initially available, right? So everything is predicted using the 17 tokens only. Does that make sense? You should use it is what you are. Okay, so the question is that ideally we should be using you should be doing a sequential decoding, right?
Because it can depend
It can, right? But that's what. So what you're saying is that I'm making your task a bit harder. I have given you some 17 words, right? Now you predict using that. I know that 3 words have been hidden, but you should be able to become smart enough to predict these 3 words from the given 17 words, right? Now, otherwise it would just have been, hey, I've given you some 19 words out of 20 words and predict 1 word, right? So that is not as hard as saying that I'm going to take away more data or more information and you should still be able to predict it, right? If it's still able to predict, then only it is really learning about the interactions between words in the language, right? So that's the idea. No, so that's how you're not setting up the problem, right? Yeah, you're setting up the problem as some k percentage of the tokens are masked. These k percentage of the tokens have to be predicted given the remaining 100 minus k percentage. So now we have to find out ways of masking the word because this word cannot be fed in the input, right? If I just feed the sentence, I like to read a book, and then I ask it to predict the second, fifth and 10th word, there is like, obviously it's a trivial problem, right? So you have to mask these words. So these words have to be deleted from the input and then produced at the output, right? So how do we do that? So let's see, right? I mean, we will first try to sort of draw an analogy for what we did in the decoder only models, where again you did not want the words to see everything that comes afterwards and you had used a mask there, right? Here also it looks like there are some words which you don't want to use, then maybe you can again use a masked attention, right? So let's see what if that idea makes sense, right? Our objective is to mask a few words randomly and predict the masked words. So maybe I'll just replace these words by the mask spatial symbol, okay. Now can we mask the attention weights of the words just as we do it in causal language modeling, right? So these, in the causal language modeling you had this situation that you had seen some I words and then you are predicting the I plus 1 word. So you are masking out everything that comes after this and you are doing this with this mask matrix, right, the triangular, upper triangular matrix which had all infinities. Now can you do the same thing here, right? So here you have a situation like this, where the masks are not sequential, but they are appearing at random places. So now can you have these places set as infinity, so that their contribution in the attention weights is 0, right? So that's the first solution that we are trying to propose, and let's see what that means, right? You see the analogy between the two. There you had like a sequence of tokens which you wanted to mask out, so you used a mask matrix. Here you don't have a sequence of tokens, you have some intermediate tokens, so why don't you mask out those tokens, right? So this is the mask that I could introduce, right? Suppose I wanted to mask the first word and the second last word, then I'll just have a mask matrix which gets multiplied with or added to the attention matrix that we had computed, and then these weights will get zeroed out. Does that make sense, right? Now we cannot do that because we want the model to learn what the blanks are, because we want the model to know that these were the blank words, right? So you pay attention to that these are the blank words and then you try to predict in the output. So you want them to know that these are spatial blank words, you don't want them to sort of get removed from the equation. So if you zero out the attention weights, then it is as good as these words don't exist. But you want those words to exist and the model to know that this is a mask and now go and predict what the actual word should be. Does that make sense, right? So that's what we will do here. We want the model to learn what the blanks are, we want it to attend to the blanks. We can then think of masking as a process, right, which is going to sort of corrupt the input. I think this is what my initial input was. Now just think that I have replaced some of the words by a noise, that I've just, the equivalent of an image would be that I have blackened out certain portions of the image and you want to predict those portions of the image again, right? And then the model has to recover those. So we cannot use this masked self-attention, we'll just use spatial tokens called mask tokens, and we'll introduce this new token in the vocabulary, just as I, you, me, water, air, all of these are words in your vocabulary. Mask is yet another word in the vocabulary, and you will just replace some of the tokens by the mask token, right? So the input to the transformer is now I mask something something mask something something mask, right? And it will pass it to the encoder. What does the encoder do? At every layer it produces capital T representations till the last layer. So till the last layer you have got capital T representations, and at the last layer at the appropriate points you want to predict what the actual word was, right? So let's see what that means. So this is what is going to be the input. Mask enjoyed the mask transformers. Then this is the full, suppose we had only one layer, right, and we can just extend this to n layers, right. So, if we had only one layer, then at the end of this layer you will produce as many representations, which is capital T representations from the output of the transformer block. Even if you have capital N layers, the nth layer will produce capital T representations. Of these, you are interested in two of those, right, the words which were masked. Here you want to predict a distribution over the vocabulary and maximize the probability of the actual word which was present there during training. Is that clear? Okay. So, these two words you will predict a distribution over the vocabulary and try to maximize the probability of the correct word. How do you know the correct word? Again, the same logic as what we had in GPT. You have this large text corpus. So, from that you can randomly blank out words, and hence you know what the actual expected output is, and you can just try to predict that actual expected output. Is that clear? Right? And then your loss function is just the maximizing the log likelihood of all the masked out words such that the probability of the correct word there is maximized, right, the standard cross entropy loss function. Okay. So, note carefully that only a set of m words is masked, right, you do not mask out all the words, of course, otherwise how will you predict anything, you need some context to be there. So, now the question is how many words to mask, right. So, typically 15% of the words in the input are masked, right. So, if you have an input of 20 words, then 3 tokens would be masked, and this again the more you mask, the more harder the task becomes, right. So, empirically they chose 15% as the amount of masking to be done, and yeah, as you could see, right, if you do very high masking, if I mask 85% of the words, then there is no way I can just use 3 tokens to predict what the remaining 17 tokens are. So, my loss, it would be very, very high. I will take a lot of time to converge, if at all, right. So, that would be very difficult. If you mask very little, suppose you mask only one word out of 20 words, then predicting that would be very, very easy, right. So, you need to have some degree of masking, and empirically it was chosen to be 15%, but of course, there are follow-up works which have some inputs on how much masking to do and so on, but at least in the traditional BERT model, which as I said was popular for many years, the masking, standard masking was 15% of the tokens. Okay. Now, the BERT model, which is based on, which uses the causal language modeling, is an encoder only model which has this multi-layered transformer encoder architecture. How many layers? So, the base, they had several, it was a family of models. So, the base model was 12 layers. I think they also released another model which was 16 layers. So, the base model had 12 layers and each layer had 12 attention heads. They used 15% masking, as I said. Now, the words which are masked, right. So, there was again a choice to be made for that. So, you have decided, suppose you had, let me just take a slightly better number so that it is easier to relate to it. Suppose you had an input sequence of 200 tokens, right, and you have chosen 15% to be masked. That, what does that mean? That 30 words would be masked. Of that, 80% words, that means around 24 words, not around, exactly 24 words would be replaced by the masked token, okay. 10% of the words, which is 3 words, would be replaced by some other random word, right. So, just suppose the original word was cat, you just pick some other random word from the vocabulary, it could be and, the, whatever, it does not make grammatical mistake, grammatical sense, does not matter, you just randomly substitute a random word, and in another 10% of the cases, you keep the original word as it is, okay. So, this is what they had chosen. Now, the question is, why do we do this? You said I am going to mask, and then again some 10% of the words you are actually not masking, right. So, why would you do that? So, in that case what you are doing is that this was actually fed in as I, and here again you had to predict I only, right, because in this case you just kept the original word as it is. So, suppose that was this word which was originally I, so you are going to feed in I and then you expect to predict I at the output again, and similarly these words are also looking at I, right. So, they have more information. Why would you do that is the question. So, we will we'll answer that question. So, when you are adapting this BERT, right, to downstream tasks, now we had seen earlier in the case of GPT that after you have pre-trained the model, you can adapt it for question answering, for sentiment analysis, textual entailment and so on. When you are looking at those tasks, you won't have masks in the input, right. I won't say that it was mask yesterday and then the ground is wet, right, and I want to know whether the first sentence entails the second sentence. I won't give you this kind of an input. I would give you the input that it was raining yesterday and the ground is wet, and I want to say whether the first sentence entails the second sentence. So in a real input, I will not have masks, right. So that's why they wanted to make sure that they also account for the situation where your real input does not have masks, it's actually the correct word there, and that's why they put this, that 10% of the words which you have chosen for masking will actually have the original word itself, so that at test time it can deal with the situation where you have an original word and you want to predict something using that, right. So that's the idea behind this. Okay. Now the other question was that if you just have the masked language modeling objective, is it good enough for all the downstream tasks that you might be interested in?